Hello. Can you hear me? If you can hear me, please thumb up. Give me a symbol. No? 哎，线上的同学有听得到我声音吗？如果有的话，可以给我一个赞，或者是好，谢谢，很棒。Okay. So the average of this midterm 2 was 74 or 75. Yes, this is about right. So for your reference, 90% of the classmates in this course can pass this course based on the past experience. All right, so 90%. So if you are not in that range, please make sure that you can put more effort next time. I mean, next week, final exam. All right, next week will be our final exam. And then today will be our last lecture that we can see each other. So I'm really grateful that we have this kind of opportunity to meet up in this semester, and we had a really good time. Hopefully for you, I had a good time. Yeah, thank you. And so this is the last 3 hours. Oh, by the way, between 9:50 to 10 past 10, this 20 minutes break. If you have any questions about your exam sheet, please just respond to the teacher assistant during this 20 minutes. All right. If you don't have any, I mean, no later than these 20 minutes, no letter change. All right. Okay. Thank you. So we will continue our lecture because we need to finish this PDF within these 3 hours. So a little bit time pressures on us. All right. So last time we took the final chapter, the final PDF for this course is the heat capacity of solids. Finally, we found we're going to talk about solids, although this is called thermodynamics in solid. But yeah, as we kind of mentioned that this course is mainly focusing on classical and statistical thermodynamics, a bridge between them. And now we're going to conclude our lecture by using this chapter, heat capacity of solids. So CV for solids, typically Dulong-Petit propose that all the solids have CV around this value, and this value is actually 3R, okay, because 3 degrees of freedom for each atoms, and they oscillate with the 3 degrees of freedom. All right. Later you will know that why the each atom has 3 degrees of freedom. All right. Later we will talk about this. And then they said CV is at this value. However, there's some mistake, mismatched. When the temperature goes down, goes to really low, it's not fit to that value. So we are going to see if there's any model, there's any theory that can explain this. And the first model, well, maybe it's not first. I mean, the first famous model mentioned in this textbook is Einstein model of solids since 1907, and he assumed that all the atoms is like vibrate like a oscillator or like a spring. All right, and all the spring oscillate as a quantum harmonic oscillator, and all of them have the same frequency. Of course, you know that this is not correct, right? This is not correct. But the ends can just borrow this quantum mechanics theory conclusion that assume that the oscillator of each atom vibrate in this manner, in this behavior, okay? And with each of them has the equally spaced energy level, all right? So last time we talked about this. And now let's take a closer look for this, okay? So the model is actually, we call that bead spring model of a crystalline solid in 3D. All right. So you can see that all the solid, as you can imagine, that they are aligned by the atoms, right? The atom like this. Okay. And so we can say this is bead. Bead is a dodo, okay, beads. And also the spring connecting between them. So you can imagine that each bead has spring connecting them in the at the front and back and left and right and up and down. So 6 directions, right? So, but however, because each springs shared by 2 atoms, so averagely each atom have 3 springs, right? Averagely. So 3 atoms. Sorry, 3 springs. So you can imagine that n oscillator for n over 3 spring, 3 n over 3 atoms. And atoms can oscillate in 3 independent direction, of course, moving backward and upward. Backward and forward and up and down and left and right. So 3 independent directions. And you can say, or n atoms for 3n oscillators. All right. So n is the oscillator and atoms are kind of 3 times different, right? So either n over 3 or 3n oscillators. And you can imagine that each each spring has 2 degrees of freedom, potential energy and kinetic energy, potential energy for each springs. And each atom has 3 springs, so each atom has 6 degrees of freedom. Okay, that's how we do that. And harmonic oscillator with potential energy function in the form of half kx squared. Of course, you can see that quite oftenly, right? It is you learn that in your senior high school, right? This is spring, so the ks is spring constant. So, and also, I don't know if you learned that before. F, the frequency, the natural frequency, can be determined 1 over 2 pi ks divided by m. All right. So the frequency, the oscillating frequency, natural frequency, 共振频, okay, is related to, is in this form, okay, it's related to ks, is a constant, spring constant, and also the mass of the spring or of the bead, okay. So you can imagine that if you have harder spring, higher ks, you can vibrate higher frequency, okay. And also you can imagine that lower mass, smaller mass will increase the frequency. You can imagine that if you have really heavy beats, of course your vibrating has lower frequency. So it's quite straightforward, right? So just introducing how the frequencies related to its constant, spring constant, and also its mass. All right. 好，爱因斯坦模型呢，它主要其实就是一个豆豆跟弹簧的模型。然后你可以想象这个豆豆就是 atom 嘛，哈，这个 atom 呢，它有前后左右上下6个弹簧，然后这个弹簧呢，一个弹簧都被2个 atom 2个原子去分享，所以说平均来说，一个 atom 会有3个弹簧。好，然后一个弹簧有2个 degree of freedom，自由度就是位能跟动能，好吧？好，然后所以说你有3个，就是总共就有6个自由度对于一个原子 ，OK？那你可以想象，一个原子就等于是可以在3个方向振动嘛，哈，前后左右上下，然后一 n 个振动子会等于就是你就可以想象，刚刚不是说一个 atom 有3个振动子嘛，所以说你可以说 n 个 oscillator 会有n 个振动子会有n个原子，或者是反过来说，你如果有 n 个 atom 的话 ，n 的原子的话，你就会有3n oscillator 弹簧 ，OK 啊，所以这其实就是都可以了哈。那通常我们会使用这个哦，通常因为你会有 n 个 atoms 嘛，所以你会有3n 个弹簧。然后这边有说，弹簧的话，其实动能就是1/2 k s x 平方 ，ks 就是弹簧常数 ，x 就是它的叫什么位移嘛，哈。那这个我们高中都学过了。那我不知道大家高中有没有学过这个啦，哈。我是有，我不知道其他的有没有哈。就是这个年代有没有？就是共振频率，弹簧的共振频率其实是跟它的2π1根号 ks 除以 m 相等，哦，这就是它的共振频。那是什么意思呢 ？Ks 其实就是 spring constant 嘛，就是弹簧常数，越硬的你就想让它可以振动的越快，越轻的弹簧或是连接在上面的重量越轻的弹簧就可以振动的越快，其实这还蛮合理的嘛，所以一个是在分子，一个在分母。Okay, so that's it. So let's take a closer look. 3D oscillators. You can notice that this is 3-dimensional now. So what is its U? Let's take a look. So we understand, we have learned that 1D oscillator, 1D oscillator, we know that this equation 15.8, and we also learned that in the previous PDF 8, okay? So we learned that, no problem. We done that before, okay? So we have 15.8 before, but this is for 1-dimensional. Now, it's 3D, so it just simply times 3, okay? For 3-dimensional. 3-dimensional. All right? 3-dimensional. So, previously we know z equal to this one, and u equals to u equal to this one, and then we do the natural log, okay, for z, and then we can get u. So we can get the right hand side of this formula, and then we times 3, and then because previously it's 1D, it is now 3D, so we times 3, okay. And we're now writing down theta E Einstein model. Previously, we say theta V, right? But this is for 1D oscillator. But now we go into 3D, and then we are going to explain it as a interpret it as a Einstein model. So we say theta E, okay? And again, h nu over k still the same. So theta E is the Einstein temperature, or you can say the characteristic temperature for Einstein model. All right. So CV is the U differentiation, right? So we differentiate the upper part of this page. We have 3 NK theta E over T. And actually, you have seen that before, right? So we we have seen this before. -1, 2. Okay, so again, please compare it with equation 15.9. All right, so previously you see you can compare this equation with equation 15.9 because 15.9 is for one-dimensional. And next one, 15.9, sorry, 15.8. And then next equation, 15.9, is also the CV for 1D oscillator. But now you compare with that, you notice that this only the only difference is 3, the factor. All right. So now you have the CV in this ugly form, but we can analyze it by putting the condition in it, high temperature and low temperature. So high temperature, again, you know that theta E over T, theta E over T is much, much less than 1. Okay? And then what will we be? You can follow PDF A, page 10. And if you remember what we taught in this page, and you can substitute this result into the equation, and then you will get the last few term become this. Okay, so the last few term will become this one. All right, and then you see that they can be cancel each other, so it becomes 3nk. Okay, so the back things you can obtain that 3nk, and 3nk is also equal to 3mr, right? But n and m, well, it sounds the same, but it is, the first one is capital, the other is small letter, right? 3nk equal to 3mr. Okay, the 3mr is Dulong-Petty value. Okay, so it agree, right? Agree with the Dulong-Petty value. 3mr. So Einstein model is good because it satisfies the normal condition, which is high temperature, right? But how about low temperature? Low temperature, it tells us theta E divided by temperature much, much greater than 1. Okay? And it also tells us the exponential theta E over T minus 1. The minus 1 part can be neglected because theta E over T is much, much greater than 1. So exponential of the greatest, a really, really big number is compared, can ignore the effect of the 1, right? So 1 can be ignored. And you can see that the answer will be CV approximately 3nk, and wow, ugly form. But it's okay, because this is actually our old friends. It's a green part. It's a green part of the, we mentioned that function in PDF 8, right? Remember that it has a relatively, when the temperature, when the exponential become big, become great, it will go to 1. So sorry, 0, 0. Okay, so these things become really big. It will make the green part 0, right? So CV going to 0 when the temperature going to 0, because going to 0 makes this one big. and then this one big make this one 0. All right. So again, PDF 8, page 10. All right. So yeah, page 10 of PDF 8 is quite important, right? We use that quite oftenly. So CV divided by N depends on theta E over T, of course. Okay, so theta E over T will change the CV values, right? 好，这一页我觉得还蛮关键的哈，就是说我们刚刚讲说都是三维的振动值吧，或是三维的弹簧。那之前的一维弹簧，我们在15章里面的15.8的时候就把 U 算出来了。好，那时候的 Z 在这里，那时候的 U 应该说 U 本来就在这里，然后长这样嘛哈。那我们那时候的 Z 就会造成现在这样的 U 会长这个样子，但是那时候是一维嘛，好，现在三维，所以乘个3就好了。好，所以你可以跟15.8这个式子比较一下。好，那这边原本是写蒂塔 V 嘛，哈，因为是 vibration， 但是现在因为是三维的振动值，而且是爱因斯坦的模型，所以我们这边写成爱因斯坦的开头1。好，一样还是 h nu over k， 好，这是长得一模一样，反正都是振动值嘛，哈，都是振动频率在决定这件事情的。好，然后呢 CV 的话，其实就是把它做微分，微分完以后长这样子，很丑。好，那跟15.9比较一下，15.9那也是一维的 CV 嘛，哈。好，那长这样子，长这样子，那很丑，但是没有关系，我们就看分析它高温的时候跟低温的时候的现象是怎么样，的行为是怎么样。好啦，那高温的时候表示说西塔 E over T 是远小于1的，那远小于1的时候会造成这边有什么样的状况呢？什么样的状况？就是后面这个式子会变成这样子，也就是说，还记得吗？那时候1x 减1，如果 x 很小的话，它会让这边刚好变成这个的就是西塔 E 除以 T 嘛，所以你这 PDF 8的第10页很重要又用到了，把这后面这一块变成长这样，那这样子就消掉啦，就变成1，所以变成3nk，那3nk 就等于3nr，这个 n 跟 n 念起来一样，但是一个是大写，一个是小写哈。那 n 的话就是颗数，那 n 的话就是要除以它的摩尔数的颗数嘛哈。所以呢3nk 跟3nr 是一样的，那我们算出来答案就刚好就是杜隆与贝蒂的那个值 ，OK。好，那得到这个值以后，我们就会发现 OK， 爱因斯坦的模型在高温也适用 ，OK。应该说你新创一个模型，你总是要就是原本就对的地方你也要对嘛，对不对？好，那接下来原本不对的地方你也要对的话就更好啦。好，所以呢 ，for low temperature 在低温的时候呢 ，Q 西塔 E 除以 T 会远大于1，那远大于1的话就会造成这边超大，那1的话根本就是小 case 可以忽略，小 case 忽略的话呢，那这边就变成这样子了。那这很丑，不过没关系。绿色那部分还记得吗？绿色的部分它以前是这样子，就是那时候是这样的式子嘛，哈。如果值越大的话，这边就会趋近于0。那正好西塔 E 除以 T 会超大嘛，对不对哈？所以说它就会让这边绿色的地方变成0，那 CV 就会变成0啦，所以它的确会让就是这样子的式子的确会让 CV 固体的 CV 在低温的时候趋近于0，高温的时候趋近于杜隆派地的这个值 ，OK， 很棒。So let's continue. So Einstein solids, because it interpreted by oscillator, right? So the oscillator has the frequency. Previously, I wrote it down F, but now it's become new. They are the same frequency. Okay, frequency. The frequency, I explained that before. For the kappa is force constant. Mu is a reduced mass. Remember that why I write down reduced mass, because actually remember that the rotation, right? The vibration has the mass and mass maybe M1 or M2, right? Maybe M1, M2, M1 or M2, and its reduced mass corresponding to their center of mass will be mu. The mu is reduced mass. Remember that, right? And kappa is the force constant. Also interpreted as the spring constant between the imaginary, right? So you can see that lighter mass of the spring or vibrator, you can have higher frequency, right? So here I just conclude that, write it down. Lighter atom or lighter element will produce harder crystal. So you can imagine that lighter has a higher oscillator and also corresponding to the higher kappa. Kappa is force constant. So which means that the vibrator or the spring has stronger bonding. All right. And also we can examine that if theta E over T is large, what does that mean? Which means that it has low temperature case. Okay. Low temperature case, all the atoms are in the ground state, and the vibration degree of freedom are not excited. Okay, so CV goes to 0, no value. Okay, but for next, theta E over T is small, which means that we have high temperature. The high temperature, it makes it activate all the degree of freedom. So the value is close to classical theory, which is Dulong-Petty value theory. All right. 这一页蛮简单的哈，都讲过了哈，就是说你的振动就跟你的频率跟 kappa， 也就是你的弹簧常数跟你的质量有关。好，那质量它这边写的是 reduce mass， 那为什么会写 reduce mass？ 还记得我们那时候讲到这个 reduce mass， 其实在讲那个叫什么惯性矩转动的时候，转动的惯性矩的时候 ，n1 跟 n2 它其实可以写成一个 reduced mass 对于它的时薪啊，那所以说那时候已经算出来了哈。那总之你可以看到，刚刚也讲过，就是轻的就会让它变得更高频啊。那高频也意味着就是说它其实它们之间振动的弹簧的叫什么？弹簧常数更强壮、更大。所以说 lighter 轻的元素通常会造就比较硬的材料。OK。好，然后呢，西塔一除以 T 是，接下来我们就看大小哈，西塔一 T 爱因斯坦这个温度跟 T 跟温度爱因斯坦温度跟温度的真实温度的比值啊，比值如果是大的话，表示说其实你是在相对来讲比较低的温度的话，表示说它的自由度是没有被激发的啊，没有被启动的，所以它就是0。当然如果是高温的话，就启动了。那都启动的话，表示说就符合我们的传统热力学的值，那就是杜隆 Petty 的值嘛，哈，3N 啊。OK， right. So let's take a look. Einstein solids is it's good. It's good. It's good model. It's a good model. But is that perfect? No, it's not perfect. All right. So which means that Einstein model has some problem. What is a problem? Because it assumed that a single frequency of vibration for all the 3N oscillator. So which means that although the high temperature is good, but if we plot that value you can see that in the low temperature, Einstein model producing lower CV compared to experiment. Okay, so experiment measurement has higher CV compared to the predictive value of Einstein model. Okay, so this is not really good. Okay, so here you can say this region is actually enlarged. Okay, enlarged. Right, so it's enlarged, and then you take a closer look. You see that Einstein model cannot predict perfectly at the low temperature. And it is because it assumes single frequency for all the oscillators. So next, the BI model will try to correct it. Okay, try to fix it. So this is a problem that we're going to tackle down in the next few sections. And also, I would like also want to introducing the so-called corresponding state. I will introduce a terminology, new terminology for you. It's called corresponding state. What is corresponding state? You can see that the CV is actually determined by theta E over T, right? So this is a ratio. This is a ratio. So different material may have different theta E. So even at different temperature for different materials, they may have the same ratio. Okay, so for example, this is the ratio of T over theta E, right? So even different material, for example, Cu and Ag, all right, these two material are different, so they suppose don't have the same identical value of theta E, right? They have different theta E. But if their ratio at different temperature, but they have the same value theta E over T, you see this one and this one, all right? They have the same theta E over T, T over theta E 1.5. So even they don't have the same theta E, as long as their ratio are the same, they can put in the same point in the figures. So we call that corresponding state. Okay, so it doesn't matter, just a terminology that introduced to you. OK， 好，那我们要讲的就是爱因斯坦 model 呢很不错，它高温的时候很棒，但是我们发现有个问题，在低温的时候没有到很棒。如果你今天把那条线啊，就是把它从高温到低温用 Excel 把它画出来，然后跟实验的值来比，实验值就是这些点啊，这些点，不同的材料在不同的温度下量测出来，量测出来以后呢，就发现量测的值会比爱因斯坦模型预测出来的值还要高，也就是说，爱因斯坦 model 其实没有到完美。OK， 那为什么不完美？其实很简单嘛，因为它只考虑同一种振动频率。你可以想一下，一个材料怎么可能从头到尾，从左边到右边，全部的振动都是同样的频率呢？这是不太可能的事情，一定会有一些分布啊，或是一些不同的方向啊，等等。所以说，这个就是它的失误的，也不是失误，就是不完美的地方。我们接下来的杜拜模型就会考虑进去。OK， 好，那所以这就是它的问题。那另外我要跟大家介绍一下这个东西叫做 corresponding state， 相对对应的状态。这个对应状态其实就只是一个名词啊，不是很重要，但是我只是觉得还蛮有趣的，就是说它在不同的材料，例如说银啊或铜啊这两个材料 它的西塔一绝对不同嘛，对不对？哈，那西塔一不同的话呢，那可是我们这边都看的全部都是西塔一 over t 这个比值啊，哈，就是你材料参数跟你现在温度的比值。那即使两个材料的西塔一不一样，但是只要它们的西塔一除以 t 的值是一样的，那你就会画在同一个图在同一个位置上，即使是不同材料，它会得到一样的值，哎，蛮酷的啊、哦。那还真的嘞，对不对哈？还真的是这样子。所以说CV 这个东西真的是跟西塔一除 t 这个比值是相关的，而不是跟温度完全相关，它是比值相关，所以这还蛮有趣的。OK, next one we can have a practice example, right? So the example is the partition function of a system that obey Boltzmann statistics. Okay, Boltzmann statistic, you can see that when you see Boltzmann statistic, you can say this is an oscillator. Oscillator, okay? And another you can see that this is an oscillator is another hint is that E. Okay, so when you see it's a partition function Z equal to something, and the something containing theta E, you say, oh, this is the Einstein model. Okay, so yeah, it's talking about three-dimensional oscillator model. All right, so when you see that, okay, and then where A is a constant, okay, and the theta E is equal to h nu over k, no problem. Calculate UPF and CV. Let's take a look. When you see this kind of problem or example, when you see the formulation of Z, the first thing that you are going to do is determine its natural log Z. This is the first step, okay? Because natural log Z allow you to obtain U internal energy. So the first things I will do here. Okay, so natural log A plus 2 natural log V minus theta E over 2t. So this is natural log Z. So now we are ready for U equal to nkt squared partial natural log Z partial T V. Okay, there's a really important things that don't forget this because this is three-dimensional Einstein model. You have three-dimensional oscillator. All right. So now, from now on, it's just normal calculations. And remember that, wow, final exam may contain many of calculus. Okay, I know this is kind of difficult, but I'm sorry that it is required. Okay. Theta E 3mr theta E over 2. Okay, so this is U. So don't forget this 3. Otherwise, everything is the same. All right. And next, B is P. Well, but be careful, okay? Be careful because maybe it's not best order for you to solve this problem. Actually, P is actually can be obtained from the P is pressure, right? But the P is actually best to calculate F first. Remember that, right? So you need to be careful. Although the order is here, PF, no, you should determine F first. And if you are going to calculate F, you should calculate S first. All right. So, wow. So I will continue our lecture and explain this further in more detail later. All right. So if you have any question, just let the teaching assistant know if you have any question for the exam sheet. All right. So I will see you after 20 minutes. Thank you.
哎，期末考教时间。
哦，好，辛苦了。好，谢谢。哎，
这个是这个
没关系。
这是2题。
哎，对，2T，你说的是对的，厉害厉害。Sorry，哎，等一下，不好意思，2T，然后请给我你的号码，3136131025，谢谢。好，请说。哦，这个，
西塔，
不好意思，西塔1除以 T， 哎，是要 T 除以2T 了。
所以这个是没有的。
哎，
我想
对，你说的对，我不好意思，我都不知道在干嘛哎。对你说的是对的，因为我在干嘛？我在干嘛？对不起，我的脑袋有点问题。对不起。
这个2T 是怪怪的。
对，没有错，不好意思，他先讲了，
好，
我已经改了。
好 ，OK。
对不起，
好，
我先让大家看一下我写错的部分。
先倒掉。
没关系，倒掉就倒掉。哎，谢谢，
对，
谢谢。哎，打了。
如果用这是对，这是单的。 我没看到一个这个。正常，请问一下，一样的答为什么会扣扣一样的答是这样。另外呢，
前面这里我加强更多就是那怎么遇到加强更到底是要
这就说，如果今天把因为对它虽然它的意义就是意义是整个人，因为机会然后这个摆这个sorry 对你说对对。有在里面的 sorry， 也是。我那时候只有那个等一下，20号，就是最后是一个人的什么的，我比较这个微信会挺大的问题。
所以这班就是不能开始。然后在那就是我劝我要讲的。
所以我改5.01，然后大家都被扣2分，这样是好的吗？因为那题真的是只能是
没错，没有，我刚有讲说就只能5啊，对，不能超过那个。
好，谢谢。
Argument for your journal publication. Open page.
他也跟我们写一样的，对头。我看看你这个。那个政府就会放，因为我毕竟这个非常差，这怎么说？一句话会听到，所以这目前大家都是有知道的。分两个，稍微有点东西，个别东西的，然后有些东西的一个很传奇。总不要太过说啊，你说全部是对，然后没有钱也差不多的，这个我就点那没有第一个，我就就是这边有个造的那个那个公司有点是不能因为你有个放的那个还有什么多的人跟你啊，就是他们的人啊，那个是。最近大一个这个我们要什么？这个还是怎么？就是没有人这个专家。那我知道了，
他说很哦，就是一个实体店家庭。要怎么说？因为它需要有电珠什么之类需要加进去。哦，可是2000感觉有点好。但2000其实也偏贵一点啊，它有在涨价啦。
就是考虑。
And the yeah. I guess so. It's not going.
OK 吗？OK 吗？好，谢谢。诶，
Okay, welcome back. So let's continue our lecture. So I'm really extremely sorry that I don't know, my head was not clear enough that I made a mistake here. All right. So please correct this, and thanks students here. All right, so let's continue. So after we finish a determination for U, and then remember that we have the three-dimensional, all right? So we have three here. And then the problem asks us that P and F and CV, right? But as we know that if we want to calculate P, we need to calculate F first. And then if we want to calculate F, we need to calculate S first, right? So PDF 7, right? So firstly, we need to calculate S. However, we are not going to, I will leave this to you. This is actually problem 15.2. And then 15.2 will ask us to determine S by using similar manner. All right. Well, it's not corresponding to this Z, but it requires us to calculate the S according to the oscillator. Okay, 3D oscillator. So what is the S equal to S for the 3D oscillator, which is S equal to K natural log W, right? And then you can go for F. See PDF 6, page 23. All right. So you know that how to you know how to do that because we have taught that before. Okay, but this is a little bit difficult, and a lot of your senior asked me how to determine this. All right, so I can give you a hint to determine this because you know one-dimensional, but this time 15.2 SU three-dimensional S. So three-dimensional S, you need to do two difference. Well, two things you need to focus. Okay, the first one is previously one-dimensional is N. Now you become 3M. That's you understand this, of course. So previous one-dimensional, now you have three-dimensional, so you time 3, just like this. However, this is really, really important. When you talk about the K natural log W, you need to also calculate, you also need to consider the degeneracy, G. One-dimensional degeneracy, G. What do you think? What do you think if the one-dimensional oscillator is G? How about three-dimensional oscillator? Again, G, not 3G, because each oscillator still has G degeneracy. Because the direction for the dimension, three-dimensional, is one-dimensional for oscillator, the other oscillator, the other oscillator. So three-dimensional, 3 times number of oscillator, but each oscillator degeneracy are still the same. All right, so this is really difficult. So,
老夫，
嘿，
那个画面好像没有切回那个平板上面，那个对，
哦，
线
不好意思
上的画面，
谢谢国平，这样可以了吗？
哎，现在还是没有，
还是没有吗？
对，看到的是那
诶
个视讯镜头的，
好，对不起，那这样 OK 了吗？好像
可以
有我的荧幕了哈。
对，
好，谢谢你。那我再分享一次，OK 吗？
OK，
好，谢谢国平。All right, so okay, I will quick go through it because we are going to determine P, but we need to determine F first. If we are going to determine F, we need to determine S first. All right, because it's according to the PDF 6, page 23. Determine S and then go to F and then go to P. Right. However, the problem 15.2 is for three-dimensional model, right? But PDF 6 is for one dimension. Okay, and now I can give you some hint to determine the S in the three-dimensional model because three-dimensional, our M become 3M. Okay, for each atom, we have triple number of springs. However, each spring has the same degeneracy, G. It's not because it's not going to multiply 3 times, okay? Because each oscillator is still the same oscillator, all right? So this is really important. S, N to 3N, G to G, all right? And then you can obtain your S, the problem 15.2. And then you can get minus 3 NKT natural log Z. All right. So this stuff is come from S and then go to F. All right. So this is you shouldn't memorize it Okay, because if this is not Boltzmann distribution, then you may go for another, and you may result in another result. All right. Then this is pure calculation. Natural log A plus 2 natural log V minus theta E over 2t equal to minus 3 nkt natural log A V square minus theta E over 2t. Right, that's it. That's it. So your F done, and then you are ready for P. 3 nkt partial natural log Z partial V T T equal 3 nkt times 2 times 1 over V equal to 6 nkt divided by V 6 nRT V. Okay, so well, this example is actually the most important thing I'm going to emphasize here is that you need to learn how to jump from one-dimensional to three-dimensional, but it's not always just times three. No. Sometimes you need to consider more choices, and the degeneracy are still the same. So you need to be careful. Okay. So EFS. Then the final one, D, is CV. Partial U over partial T V equal to partial 3 over 2 nk theta E V partial T equal to 3 over 2 nk partial theta E over partial T. And we notice that theta E over T is not related to V. So we can take out the V here because not related to V. Okay, so that's the result, the answer for the problem example mentioned here, right? 我最近看到就是就有其他的同事啊老师跟我分享他的教学文件啊然后上面他说他的那个教学的那个评价上面写说他的那个讲义，然后填空让学生不太开心。我心想啊，我填空，我也是填空啊，那你们会不开心吗？对，我很担心这件事情。对，所以 但我觉得填空才可以让你们有那个有不会睡着啊。我虽然还是会睡啊，但我意思说，就是才会有事做嘛，对不对？所以其实我也不知道很多教学的方式，但是每个老师适合的就是也不太一样。这样，像我就很不适合那种来啊，大家一起做活动啊，然后然后大家来讨论这个，我就觉得我无法就是把我的注意力放到所有每一组身上，然后对，所以我觉得这个还蛮难的哦。教书其实我觉得真的是一门学问，需要去就是看个人的特质，然后其实然后有的时候我的教学方式适合某一些同学，但是却不适合另外一些同学，这其实真的是蛮难的。对啊，我在刚开始当老师的时候，看到教学评鉴，我都会就是教学的评语，我都会很难过，就哇，学生对我的教学就是不满意啊，然后有时候甚至会人身攻击啊，然后都会很难过。但经过了10年以后，我好像就释怀了。我想说，我可能真的是无法满足所有的同学这样子。那对我就尽力做到最好，那我觉得的最好就是应该可以感觉到我的投影片我花了很久时间吧。我真的花很久时间哦。你可以看这些，尤其是这个那些都做很久了，然后挖空也挖空了，也是要对，所以说我真的是花很多时间在这里。对，所以说你看下一页也是很多东西要弄，所以希望这些努力可以帮助大家学习啦。那如果任何问题或任何建议都欢迎在评语上面写这样。那只是虽然我说我已经比较不会被伤害，但是还是不要伤害我，好不好？拜托，对不对？我们好好写啊，话好好讲啊，拜托。OK，这比较多，让大家抄久一点。那而且最后一次上课，我们也聊聊，那要聊什么？最近还真的没什么好聊的。嗯嗯，糟糕了，我已经越老越不会聊天了。我有没有讲过我以前在做人体实验的事情？在英国念书的时候，我是有奖学金的，但是奖学金只有3年，所以说，然后我又不是很会存钱，所以我前3年的奖学金就全部都用完了。但是我还没有毕业，那剩下的时候我就没有钱了，然后我就去做人体实验，去做打工，然后我就去看，因为反正有医学院嘛，然后就看那种新药的试验。我完全不敢去那里，就是你要打新药，很赚哦，那都是就是几百磅英镑啊哈，我那时候在英国念书，就几百磅都是这样打下去，你就可以几百磅，但是我觉得说这可能会有后遗症，我觉得超恐怖的，所以我就不敢去做那种身体实验，所以我就选择去做物理性的。什么是物理性的？就是我就去选择一个叫做低氧环境的实验，他就来帮我测试我的血氧在一个低气压的状态下。什么是低气压？我先想说，低气压其实就是3000公尺的高山嘛。然后我想说，我就去，反正我就觉得好，假设我去山上，那我觉得这很正常，所以对于人体应该不会造成太大永久的伤害，然后去做这个测试。那一开始真的是呼吸转哦，因为要做 control 组嘛，所以要在一般的状况下，我就坐在那边呼吸，然后1个小时就70磅，那时候的汇率是60:1， 那时候是蛮高点的，所以60乘上70，哇，就是3000多块，1个小时坐在那边呼吸，然后抽个血，3000多块就入账，好开心哦。然后呢，结果后来真的要做就是对照组的时候，我就被关在一个房间里面8个小时，然后那个房间是被抽，那个气压被抽掉，然后我就是在3000公尺的高山上的感觉，然后你不能睡觉，因为睡觉就等于是就是整个血压或什么都会降下来，我们要正常，所以我就坐在那边，我开始滑手机看书，你也不能打电动，因为打电动会激动嘛，所以你只能看书，然后坐在那边不能睡觉，也不能的，反正就在那边里面，前6个小时也是一样呼吸转，还蛮舒服的，就是没事啊就开始滑手机，到了第7到第8个小时，生不如死。哦，那高山症的状态，就好像是你晕车加中暑的感觉。我那时候真的是，哇，真的快死掉了，很不舒服。最后那2个小时，然后后来到结束的时候，我出来我都是全身发冷，然后那时候觉得说，我再也不要做这个实验了，再也不要出卖自己的身体。但是真的赚很多钱，然后我出去以后就说，哦，我千万不要再做赚这种钱。然后过了大概3个月，我再报名了下一次，因为真的没钱，我报名下一次，但不是这个，我是报名那个另外一个运动型的，它是要量测你的就是血在于斜的状态的斜的运动状态的情形，所以我一开始是上去我要去骑那个脚踏车，就是那种运动脚踏车，对，骑，然后你要冲刺哦，然后冲刺到而且那个冲刺不是说你要冲多快，是要你尽全力，反正就是要让你累到不行的意思，它就是要到你极限，要看你身体的极限，所以它就是要我冲到极限，然后量测就贴一堆有的没的在我身上，然后就量测，然后接下来就要变成45度角。你要变成斜斜的去骑那脚踏车，我觉得蛮有趣的，但一样是超累，但是这次就没有那么好赚了，因为它不痛苦，它只是累而已，所以它就没有上次那个70磅那么好赚，它可能就只有40几磅，所以说，对啊，就是你就可以用那个钱来告诉你这个实验对你来讲的就是痛苦程度哦。那打针那个东西，那个危险性太高，我不太敢啊。Anyway，蛮好玩。Right, next. So the buy model is actually, sorry, I should kind of do the translation, right? I just talk about the story about my when I study in the UK and I do the body human experience experiment for low oxygen test and for the oblique sports exercise behavior of human body, and I earned some money for leaving because I running out of my scholarship during my last year of the PhD degree pursuit course. Yeah. Anyway, fun. Now the device model of solids. The device model improved Einstein by considering the vibration is a body as a whole. I mean, they containing. I mean, they examine these things for everything, every part of the crystal, and they are not assuming they vibrating at the same frequency. Each of the vibrator may have their own vibration frequency, and this model is actually considering more realistic vibration. Okay, so when you find out the earthquake, sometimes earthquake in our daily life, if we have the earthquake, sometimes you will feel the vibration is forward and backward, or left or right, right? and sometimes up and down, right? When you feel up and down, and this is terrible earthquake, okay, just run, all right? If you have a heavy jumping vibration, it must be serious, all right? So when you feel that, all right, so you have 3 types of vibration rather than just simple spring vibration like we discussed before. So they consider that the solid vibrate like a phonon gas. The phonon gas vibrate like a phonon gas and or phonon particles. And this matter vibrate has some modes. What is modes? Just so I mentioned that jumping, the first mode, left, the second, and backward and forward, the third. Okay, so this is a longitudinal wave. You can see that the first one is longitudinal wave. So the wave propagation direction is parallel to the mass changing direction. You see, kind of vibrate like this, ding, 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 changing the position. All right, and the wave propagation direction is the same as the mass point changing their direction, right? So you see, it propagates like this, and the mass changing left and right. Okay, this is called longitudinal wave. In the second and third, the second is this one, okay, this is quite normal. The other is this. It's flat. It's on the plane. Okay, so you see there are 2 transverse wave. Why we call that transverse? Because the mass movement is perpendicular to the wave propagation direction. So the wave propagation like this, right? It go left to the right hand side, but the mass point is up and down, or left and right, left and right. But the mass change direction is perpendicular to the propagation direction. Okay, so there are 3 modes for this kind of model, for this kind of solids. So yeah, in the real world, our earthquake just looked like this. Our earthquake just shake like this one. 3 modes. So you can imagine that the model, the solids can be looking like this. All the atoms, and they vibrate in these 3 modes. Okay, so their vibration has their mode, and each mode may have its own lambda. Okay, their wavelength. OK， 好，就是the Bi model 啊，它比爱因斯坦好，它不会假设每个方向都是同一种振动状态，同一种频率，它是把它考虑成像是风弄的振动的模式。这个振动的模式跟现实生活中我们遇到的振动比较类似。我们常看到地震，有的时候会上下震动，然后左右震动，对，然后前后震动。那这样子，通常都会先上下震动，然后再左右震动，这样，然后平面的震动。那当你发现地震这个上下震动，因为它会跑比较快，它会先来，然后它上下震动很夸张的时候，表示它等下来的会更大。那如果它前面你没感觉到上下，如果它没有跳动，它表示说那也还好这样。那所以说只要你的就是上下跳动不是很大的话，那你就可以放心。但是当你发现上下跳动很夸张的时候， 先跑出去，因为等一下来的会更大。那这就等于是说，就跟这个非常非常像。好，它有3个模式。第一个模式是叫做什么？叫做 longitude， 是纵波吧。Anyway， 一个叫横波，一个叫纵波了哦。那 longitude 的意思就是说，它的波传方向跟这个指点震动的方向是平行的。你看到这个是前后震动，然后这个它是往这边走。OK， 那它往这边走的话，一个是上下这样震动，那你可以看到它的指点是往上下的，那它可是跟它的前进方向是垂直的。那另外一个是铺平在地板上的，那它是好像是左右在震荡的，那它就跟它的方向是垂直的，所以就是2个横坡的模式跟一个纵坡的模式，所以2个加在一起就会是真实的固体的震动的状态。那因为这样子的震动状态，它就会有波长的概念在里面。Okay. Now, so if we consider the phonon gas as a vibrator, we need to consider the wave function. The ordinary wave function, phi equal to a sine kx. The k here is kind of the wave number. The wave number is actually also correlated to the n. Do you remember n? N, if you remember, the n here is this one, n equal to 1, right? It's an anti-node number. And we talked this before, right? And this is n equal to 2. And remember this L, right? We talked about this, right? So remember the L divided by N equal to lambda divided by 2. We learned that before, right? So the K here, the definition of K is 2 pi over lambda. So we kind of ratio of your wavelength and 2 pi. So it's kind of phase difference things. Okay? Then you know that lambda is lambda divided by 2 equal to L divided by M. So you can substitute this one and you can get K equal to M pi over L. The N is the anti-node number. Okay? So then some common sense here. C equal to lambda frequency, right? This is common sense. And volume, we treat that as a square box. So cubic, L cubic, right? So your M here, your M can be replaced. The lambda can be replaced C over nu. Okay, so C over nu, and L can be replaced by V cubic root. Okay, so after you substitute this, then you can get M equal to 2V 1 over 3 over 6 and nu. The C is the speed of wave. Okay. Then if you have M here, you have nx, ny, nz direction. So your n square is nx square, ny square, nz square. So which means that your oscillator has so many choices, either vibrate like this or vibrate like this or higher mode or higher n. Okay, so you can imagine that this nx, ny, nz is the choices of it, and each of them need to be integer. Integer is not point something, it's integer 1 or 2 or 3. Okay, then the oscillator has so many choices. It's also known as degeneracy. Okay, degeneracy. Genu. So the degeneracy is the oscillator, the choices that oscillator can choose. So you can imagine that the point in this space is the choices that oscillator can choose. Okay, the point. So how can we find the number of the choices? Remember that previously we said if their points are all integer, the volume can be the number of choices. Volume value, because remember each volume can represent one choices. Okay, so remember that this the point on this in this surface or in this space represent this point represents the choices of the oscillator can vibrate. All right, so G nu d nu is the number of possible frequencies in the range of nu to v plus d nu. So you can see that nu plus d nu is kind of the shell, small skin of this. Okay, small skin of this surface. So the point containing in this surface is the choices within this frequency range. All right, so G nu d nu equal to 1/8. 1/8, right? Because it's a positive octave and 象限. And also this surface of area is 4 pi n squared. Is this is the area of the shell. Okay, and the n is the thickness of that shell. So you can count the volume of that shell. And the volume of that shell means that the point, how many points, how many integer point containing inside this shell. And the shell volume can represent the choices of the oscillator can vibrate. All right. So this is, and then after some calculation, and we substitute this n into this n square. So you can get 4 pi v divided by c cube v nu square. Wow. So you can see that this is G nu. Okay, because d nu. Okay, so the highlight part, yellow highlight part is G nu. Okay. Right. So if you can accept that, now this nu here is for one wave, but now you have 3 waves. 1 is longitudinal, 2 is transverse. So you can rewrite this equation 4 pi v, and v and c are the property of the wave. So you need to take then separately CL cubed and 2 longitude transverse CT3. Okay, that's how Newton square d nu. All right. So now, again, the highlight part looks like this, but this is too difficult. Too difficult. What is value of that? What is this? What is this ugly form? It's difficult. It's really difficult. So how can we proceed? We have smart ancient scientists found that they can do a trick to solve this. They say total number of oscillators is 3n, right? You know that. You know that. So this is a trick. I know that total number of oscillator is 3n. So if we can summation or integrate from 0 vibration frequency to the maximum vibration frequency, sum them up together, it will become all the total number of oscillators. This is smart. This is really smart. Okay, so you can say nu m is actually the maximum frequency from 0 to maximum frequencies, and sum them out together, it becomes 3n, the total number of oscillators. Okay, so that's the trick. So they substitute this stuff to here. Okay, and then do the integration. And then after do the integration, they do 0 to nu m and substitute the integration result. It obtained to here. Okay, so the result looks like this. This equal to 3n. Okay, and luckily, this difficult part is actually what we need, right? This difficult part is what we need. And we know this part equal to 3m. So we can substitute this ugly part by using m. Okay, so luckily it becomes 9m v squared divided by nu m. And not v, sorry, this should be nu. Nu. Okay, and the nu. So we substitute to replace this ugly part by using 3n and nu maxima. Okay, so the trick help us to do this. Okay, so this is the final result. G nu d nu equal to this one. And then one more information can be obtained here. You can notice that this stuff is actually m. So if we just move the v to the left hand side, and then we found that the n divided by v is actually equal to something alpha. Okay, nu m cube. Okay, so this is actually a constant. Okay, alpha, random constant, ugly constant. All right. So you notice that new maxima cube is actually proportional to mv. So this is how we get this. And then nu n is the maximum frequency, also corresponding to minima lambda, minima wavelength. So minima wavelength proportional to v divided by n cubic. So you can see that this lambda minima is actually the average interatomic spacing. So you can imagine that they're vibrating lambda is corresponding to their spacing between each atoms. All right. So that's it. So you can see something from these values. 好，要讲的东西是这一页我觉得蛮难的哈，跟大家解释一下。就是 the bi-model 呢，它是用 wave 嘛，对不对哈？它是用波。那波函经典的波函式就是这个值等于 a sin kx。OK， 那这个 k 其实就是我们所谓的波的。反正你知道项嘛？哦，项就是一个完整的结束，就是一个项，然后再下一个项，再下一个项。那所以 k 的话，其实基本上 sin kx 其实就等于是说你的波长跟2拍的比值。那你这个浪打在以前我们也说过啊，它的浪打会跟它的节点数波的节点数有关，所以这个你还记得吗？哈，那时候我们写过，我们把它带进去以后。我们就可以把 k 用 n 来取代。好，那 n 又是什么呢 ？n 可以 n 是等于是这个东西嘛？哈 ，n 是这个的关系，跟浪打关系这个。那浪打跟波速等于浪打乘频率嘛？哈，这是我们的常式。然后体积又会是 L 的3次方，这没问题。所以我们就可以把这个东西带入进去，得到 n 长这个样子。好。那 n 跟你的频率有关系，跟体积有关系，跟它的波速有关系。OK， 好，然后呢，这边 n 就表示说这个波可能的节点数，也就是它振动的形态。那它可以选择1到无限多种嘛，对不对？哈，好，那 n 平方当然是有 x 方向、y 方向、z 方向的，就好像是一个向量这种感觉。所以你可以想象这个 n 的选择啊，哈，可以是在 nx、ny、nz 这样子的一个的 space 的这空间里面，它因为 n 都是正整数，所以说你可以想象这边的所有的正整数的节点，就是我们的弹簧可以选择的模式，振动的模式。OK， 所以例如说了哈，111可能就是 nx 等于1，ny 等于1，nz 等于1，也就是说他们在 x 方向、y 方向、z 方向的振动模式都是第一个模态，这种感觉。所以它有很多种选择。那我们要怎么样计算有多少种选择呢？也就是我们的 G-nu 咯。有多少种选择呢？当然就是因为它都是正整数的点，所以你只要算它的体积，就等于是它的可以选择的数量。OK， 因为一个单位就是1嘛。体积一颗就是1，然后你就叠起来，就表示说它有几个点可以选。OK， 那时候我们都有讲过了哈，所以 G-nu 呢 ，d-nu 就是这个的 G-nu d-nu 就是在这一个小范围，频率这个小范围之间有几种选择，那我们就是要看这个薄壳里面的体积是多少。如果有多少体积，就表示说它有多少个选择在里面。OK， 所以我们的1/8，因为只有正的象限嘛，哈，4拍 n 平方就是它的球的面积乘不是 area， 球的表面积乘它的厚度底 n， 就可以得到这个丑的东西。好，那丑的东西，那黄色部分就是 G-nu 嘛，哈 ，G-nu。那这个东西呢，还不要忘了，我们还有一个纵波2个横波啊，哈。那所以我们必须把这个跟 c 跟 nu 都加起，就是它的那个可能性都要加起来，所以我们把这边有1跟2倍一倍的纵坡，2倍的横坡都把它分开，就是拆解开来加总起来。好，但是这个东西很丑很难算，那该怎么办呢？我们不会算，所以呢，聪明的科学家就发现，其实它有一个 trick， 它有一个就是东西它可以做运用，就是说，如果你从最小的频率到这个系统里面最大的频率，全部加总起来，就会是你的总颗数嘛，3n。好，那我们就这样子把这个东西带进去，然后从0积到 maxima，mu max 就是最大的频率了哈，最大的频率。那为什么这边说 cutoff frequency 就是它上面都不算，因为它不会在这出现哦。好，那我们积分起来以后，然后带入这个0跟 v new m 这个的上下限，我们就得到这个东西会等于3n。那好加在就是这个东西啊，跟这个长一样，所以我们就可以把这个东西用 n 来跟 n 跟 new m 来取代，就可以取代成这样，好看多了。OK， 那除了这个以外呢，我们还可以从这个式子里面发现说 new m 的3次方会跟 n 除以 v 成正比，就长这样子。那 new m 是频率嘛，那换一个导数就变成lambda 的最小值。lambda 最小值会约跟不是约，是跟 v 除以 n 的1/3次方成正比。这个 lambda minima 其实就是它振动的最小的范围。那因为最小的波长，那其实也可以想象，就是它跟它的 atom 之间的 spacing， 它的距离是有关系的。OK， 好，这一页就蛮多东西要请大家注意的。Okay, so I will give you 10 minutes. I will resume our lecture at 11:12. Thank you. 嗯，什么意思？呀？哦，对对对，没错，没错，哎，不会超过5。
Okay, welcome back. And this is our last hours, right? Thanks for cooperation, and I will continue our lecture. And I will finish the last 7 pages, which is a little bit intense. So I will, I won't talk more, right? So difference between Einstein model and the bimodels. So there's no restriction on the number of phonon per energy level J H nu. The phone, so you can imagine that all those oscillators are all independent, so they can choose the same things, right? The same energy level. So they can be treated as bosons, all right? So because they can be treated as bosons, the occupation number follow boson Einstein. Distribution. All right. So remember what is Boson-Einstein distribution. Remember that it should be mj over gj equal to 1 exponential epsilon j minus minus mu is that minus mu kt and minus 1. Remember that, right? Okay. So this is what we learned previously, right? And you notice that previously we say NJ, GJ. So this is an energy level number. But now we are not treating like this. We are treating the energy level as how they vibrate. So how they vibrate is actually, we can treat it as a epsilon. The energy level can be represented by the energy. So let's rewrite the formulation into the N epsilon form or G epsilon form by specifying the energy as a function of the parameters. Okay, the parameter of the function. All right, and then 1 over epsilon minus mu over kt minus 1. Okay, so it's still the same. Like you can see that everything's almost the same. Now, for us, we can say nu can be regarded as 0. Why? Because we are talking about the equilibrium states. All right. Why it has become 0? Because it's equilibrium state. Okay, equilibrium state. Why equilibrium state means mu equal to 0? Because our Helmholtz function has 0 T and V. We know this in our PDF. I guess it's file 4. I don't remember, or 8 or 3. I don't know. But remember the Helmholtz free function are related to the equilibrium state because the F final will always less than initial. And if you reach the equilibrium state, which means that the df equal to 0, right? And what is the df equal to 0? The partial f partial n t comma v is nu. All right, so if this f becomes 0, of course the mu equal to 0 when you talk about the equilibrium state, right? So this becomes 0, and then again, we can transform this N and G into another form is as a nu as a parameter, frequency as a parameter. Here, because when we talk about the parameter, energy of the parameter of oscillator is the frequency, right? So it's exponential h nu divided by kt minus 1. So the bimodal n nu over g nu equal to 1 over exponential h nu over kt minus 1. Okay, so we obtain this ratio. Another difference between an Einstein and the bimodal is that, as we said, Einstein model only fix one frequency. So you can imagine that in such small interval, all the 3N oscillator is locating inside this range. But the bimodal, they have choices. They have choices under maxima frequencies. Okay, so this inside 3N is 3N with inside such tiny interval for Einstein model, and the my model has a distribution in it. OK， 好，我们接下来讲就是这两个 model 的差别哈。那 the bi model 我们说过它会有不同的 frequency 就是振动的频率，那它们之间互相弹簧是不会互相干扰的，所以说它是可以选择同样的能阶、同样的振动，所以它跟 boson 是很像的。Phonon 跟 boson 哈，Phonon 就是 boson 的哈，它就是不会去跟别人排斥说它不能选同样的能阶，好，所以它是 boson。那它既然这样子的话，它就是 follow Boson-Einstein 的分布。好，那这个分布呢，还记得那时候我们写 NJ over GJ 是这样子写嘛？这边有一个减1。那 NJ GJ 其实 J 是 energy level 的 number 嘛，就是能阶的数字。那这也跟直接指派这个能阶的值也是有一样的意思啊。好，所以我们直接把这个 NJ GJ 变成一个是 epsilon 这个能量的函数。我直接指派这个能量，我就可以知道是哪一阶啦，对不对哈？所以 N epsilon G epsilon， 然后把这个 epsilon J 变成 epsilon，OK？ 那这时候我们再继续下去，我们说这个 nu 会是0哦，为什么？因为我们现在讨论的是 equilibrium state 啊，我们是稳定的状态啊，稳定的状态会怎么样呢？还记得我们那时候讲 Helmholtz function 的时候，我们说这个东西是一个 equilibrium 稳定状态的一个指标。如果你到达稳定状态的话，你的 F 就不会变化。你没有变化的话，你的 mu 当然也不会变化，因为 mu 是它的 partial 嘛，对不对哈？所以说我们的 nu 就不变，就等于0了。那这时候我们又可以再往前推进一格，就是我们的能量在振动的状态下，其实我们是可以使用频率来去决定它的能量的，所以我们就把这边的 nu 改成epsilon 改成 nu 的函式，然后 h nu 就写在这里 ，OK？ 所以呢 ，the bi model 的 n 跟 g 的比例就是可以写成这样子。那另外一个不同点在于，爱因斯坦它就是单一振动的频率，但 the bi model 就是一个范围在 nu n 以下 ，OK 的范围，它都可以3n 啊所有的弹簧都可以这样子在里面包含在里面。Okay, next one, the internal energy. When we talk about the N and G ratio, and then we can understand, we can obtain this, right? Because you see, if you make it G nu to the right hand side, you can have N nu d nu become this one. All right, so from the previous page, you can have this N nu d nu. And G nu we obtained in the previous page last hour. And then U equal to what? U, you can submit, you remember that the U is actually the summation of all the energy level times its own number, right? So you can compare these two formulation. Okay, so you see, H nu is the energy level you have. Mj is the N nu. So summation is all the integration. So this equation, these two equations is actually has exactly the same concept. All right. However, please don't forget we have 0 point energy here. You know, okay? And I believe the textbooks doesn't successfully emphasize this, okay? So you need to be really careful about this. So after we summon out everything here, and we can get ugly 9nk nu n cube 0 nu n nu 3 d nu over exponential h nu over kt minus 1 and plus 0 point energy. And you can see this is really ugly, right? Ugly. So the bi function, the bi want it take in a good form. So it said, okay, the bi defined this ugly form is du. Okay, and theta d equal to h nu m over k. So after you do the integration, so your nu m will substitute in it, right? So theta d equal to h nu m over k, and x equal to h nu over kt. All right. So after this, excuse me, after you substitute this simplified form here. Okay. Plus, you know, all right. And it equal to 3 n k t d theta d over t plus, you know. Okay. So yeah, you need to do the really terrible calculation integration, and then replace this one, and then you can see a relatively beautiful form 3nkt the by function plus you know. All right, ugly. 好，接下来我们要讲的是内能。内能的概念很简单，就是我们把所有的能阶的能量乘上占据它那边的颗数，再加总全部的能阶就好。这个我相信大家没有问题。那这个跟上面就很像啦 ，h nu 就是我们的 epsilon j 嘛，对不对哈？然后 n nu 就是我们的 nj， 那这个积分就是我们的 summation，OK？那这个 n nu 跟 d nu 怎么办呢？这个 n nu d nu 可以从前一页得到，我们把这个 g nu 移到这边，你就可以得到 n nu 啦，哈，所以就是这个东西。那 g nu 又是多少呢？我们在前页算过了，所以这个东西把它带进来，然后就可以得到，哇，好丑的东西呀，哈。但是呢，不要忘了这边的 u 有一个加 u 0哦。0 point energy 哦，这个要非常小心。课本我不知道为什么他是故意的还是怎样，他都很避免在谈这件事情，我不知道他在干嘛。总之， 这个 u 应该要加 u0，要非常非常小心。好，那总之就是做好以后呢，我们就会debye function， 就是说debye发现这个实在太丑了，所以他就自己写一个定义一个函式，说它这个底 function debye function， 然后如果用这个去代入进去的话，它就比较好看哦，好看。然后呢，这个西塔 d 就是把这些比较恐怖的东西都带入进去以后，你就可以得到这样的式子。All right， 那就比较好看而已啦哈。那它可能就等于是说，这个 d 弄进去以后，前面就是 3nkt 就很好看这样。那它就是一个很复杂的一个函式，对了。All right, so let's take a look. Let's take a look about the you know, okay? The you know, I don't know why the textbook ignore it and just ask you to do this calculation in the problem 16.2, okay? It said, give the term this one, okay? And this is constant. It's a 0-point energy. We need to prove this. 0-point energy, you know, equal to this one. And he also explained that this term is constant. It does not contribute to heat capacity. All right. So that's the reason why it doesn't want to mention it. So PDF 8, P4, we said the ground state. The ground state. Has 0-point energy, which is h nu over 2, which is not 0. Okay, so our definition of u here, you know, is h nu over 2 times the number of oscillator, right? So the 0-point energy, you can see that you need to sum them up, all the 3m, right? H nu j divided by 2 for 3n oscillators. Okay, however, this is just a concept, right? We need to do the integration. So the integration, what will it be? H nu j divided by 2, right? We can transpose that into an integration 1 over 2 h nu n 0. So we need to sum them all together. So we need to integrate from 0 frequency to the maximum frequency. And G nu D nu. All right. So our G nu, you can see it in previous page, right? Previous page. You can get G nu. And it become 9n 2 nu and 3 h 0 nu n nu 3 d nu equal to 9 8 n h nu n equal to 9 over a n k theta. D. Okay, so that's how we obtain 9/A NK theta D. So the concept is okay. Concept is not really difficult. H nu over 2 times number of oscillators. Okay. So all the oscillators summed up together. So it's half H, and then you make it half H, right? Outside of it, and this new J need to summation through all the frequency. So 0 to all the frequency, and G new and new. G new you can obtain from previous page, D new, and then you can get a lot of, do the calculation. So you see, we need to review our calculus, right? Calculus, you maybe in your first grade of your college life, right? First year of college life, and you do the bachelor degree, you need to do a lot of calculus here. I'm sorry. 好，这一页啊，就在讲那个 U0怎么来的。课本上说啊，课本一直在避免，在课文里面都避免谈到这个 U0，但是却要你在习题里面直接做，我觉得这实在太不人道了所以我就在这边讲一下就是说U0其实就是我们之前讲到的 h nu over 2，就是光 state，又讲的英文了就是最低的能阶，它的零点能量就是 h nu 除以2这个值，它不是等于0好，所以我们可以想象，在一个这样的系统里面呢，有多少个振动值，你就要乘上它的 h nu 除以2嘛就它的低点零点能量。好啦，那所以说总共的能量呢，就会是全部加总起来 ，OK， 然后有3n 个。好，但是这只是概念，我们现在必须要去做积分，因为它是连续的 nu 嘛所以呢，我们就把h 拿出来，然后要如何加到这些全部呢？就是要从0的频率加到最大的积分到最大的频率。那不要忘了积分的时候，你还有 G nu 好，然后它的 nu 本身在这里，所以你要做积分 ，previous page 就可以得到G nu 是长这样嘛好，那你就全部积分以后，就可以得到长这样的式子。那还记得吗？我们的西塔 D 就是我们的 h nu n 除以 k， 所以我们就可以把它改变成这样子，9/8 n k 西塔 D 那这个值就是这个值那因为它是常数，所以说你在算 heat capacity 的时候，它会被微分掉，所以它就等于0，它就没有任何的影响但是这课本就是因为这样子，所以它就不常提这件事情，但是实际上它也是很重要的。OK， next one， next page is 6.3, problem 6.3, but actually we have done that. So we just mentioned this next page really quick. Okay. Look at this. Okay, next page is actually the the next step for the previous page. So this one is UD, right? You know, right? You know, and they want us to practice this one, but this one is actually we have done that. All right. So I just want you to do the practice from 16.2 to 16.3. All right. And the by function. I'm sorry that they're missing a bracket here. Okay, so you need to do the u equal to 0 nu m h nu n nu the new plus you know, and you know is you obtain that in 16.2, and you need to, I encourage you to do that in your place. This is quite important, and I believe final exam will always related to this. All right. 总之这一题其实我们都已经讲过了在前面这一页就讲过了，好吗？那这个地方在前16之2我也讲完了，所以说其实纯粹这就是请大家就是要回去自己练习一下微积分，好吗？把这个东西算一下，算出来以后再再用这个debye方程去把它带成漂亮的式子。OK， 总之就是从这边开始，然后积分完以后把它带进去。好，那大家可以发现要非常多的微积分的技术。那下面2题下面2页3页我会尽量讲一些微积分所需要的技巧，然后提醒各位，然后希望大家在考试的时候应该就在回家赶快把它复习一下，考试的时候一定会考到那加油。Okay, next one is heat capacity. After we determine the U, the next one is heat capacity. The differentiation for the U will be CV, right? So after the differentiation, wow, it looks like this, very, very ugly. So how can we do make it simpler? Changing the variables, right? Theta D over T equal to H nu M divided by KT. And your X equal to H nu over KT. So if you substitute these here, and then everything become relatively beautiful. Okay? Wow, still ugly. Right, so let's continue. How about high temperature? So the high temperature makes the T here become big. So which means that X become really small. Okay? X really small makes exponential X minus 1 approximately become X. The exponential X relatively 1. So if you can obtain, you have this, you will have 0 theta D over T X squared dx, and this is 1 over 3 theta D over T3. All right, so this is this part is this part. All right, and then you can see that they will cancel each other and then become 3nk again, 3nr again. So the bimodel also satisfy Dulong-Petty equation. Dulong-Petty theory. So good. And if you can see that it's U equal to 3nkt, because if you just do the integration to reverse the CV to the U, 3nkt. So all satisfy classic thermodynamics. How about low temperature? Your low temperature makes theta D over T become infinity, because low temperature makes this one very small. So this ratio become infinity. When you have infinity, this ugly form will can be solved by appendix D7. Wow, this is really difficult, I would say. 0, infinity, x4 exponential x dx. Exponential minus 1, 2, equal to 4 pi to 4, 15. Okay, so by using the help of appendix D7, this stuff become a relatively simple number. All right, and you can say CV is this value. So you can see that this is not 0 anymore. Okay, there's actually a function like this, so it can have a proper approximation prediction for low temperature CV. Okay, and then if you want to see the U, you can also integrate it and obtain a relatively simple form of U. All right, and it's called the by T3 law. What is T3 law? It's always relative to temperature cube. Okay, so this is the T3 law. 好啊，好辛苦哦哈！刚刚讲完 U， 接下来就要讲 heat capacity 啦哈。那只要是微分它就可以得到 CV， 把前面那个很可怕的东西微分长这样子，那太丑了，所以我们就用西塔 D 跟 X 去帮它弄漂亮一点，然后弄成一个相对来讲不要那么丑的，可是还是很难了哈。好，那接下来呢，把这个 CV 长这样子，我们就用高温的状况下，高温的状况下表示说 T 要变得很大嘛，对不对哈？所以 X 就会变得很小。那边 X 变很小的话，那这个就可以变成 X， 然后 exponential 就会变成1。好，所以它就会变得比较这个东西就变得比较简单，变在这里，然后就比较好积分。积分完以后呢，我们就把这个东西蓝色东西我就可以把这个东西带进去这里啊，然后它就变成9NK 乘上我这个很丑的地方。好，然后呢，就结果发现它可以消掉，就变成3NK。哇，表示说 the bio model 跟在高温的时候也是符合传统热力学的答案 3NR。OK， 然后呢做积分的话就变成 3NKT。OK， 没有问题。但是呢，如果是低温的话呢，我们就变成无穷大嘛哈，这个比值就变成无穷大，然后这个无穷大呢就会让这个上面这个式子变成这个样子。那这个样子还是很难算，还好我们有 appendix D7 的这个式子，它就会帮我们算出一个比较相对来讲比较简单的数字，带入进去以后，我们就会发现 CV 会长这个样子，然后呢积分就变成 U。好，那这边可以看到就是说这边的温度啊哈，它就可以很明显的看到，就是它就是一个函式，这个函式在低温的状态下的时候会长这样，那它可以给the bio model 得出来的 CV 就是比 Einstein 好这样子。好，那这边你会发现很多都是 T 的三次方，所以 the bio 说啊哈，capacity 跟 T 的三次方都有关系。All right, so again, the bio function is so important, and I will just write it down and make you say du is this one, and the internal energy equal to 3 NKT, the bio function, and I do practice problem 6.4, especially the A, okay, and please go back to practice this, and then you can obtain CV in a quite ugly form, right? 好，简单来讲就是你都可以积分出来，但是呢，这边的 by function 就是让你把它变得比较漂亮而已啦，那没什么意义，但是纯粹就是说，而且你可以把它变成比较简单的 form 的时候，变成比简单的形式以后，就又可以看到你熟悉的3NKT 这种东西。然后我会建议你回去做16.4的 A， 然后熟悉一下这些计算过程。那等一下下一页就是我们最后一页，最后一页呢会带领大家温习 复习复习以前的变数变换。OK， 那大一的时候大家都有做过，那希望大家就是借由这一题可以回想起来什么叫做变数变换。All right, so this example is our last example in this semesters, and also it will lead you to review the changing variable, integrating by part, these kind of calculus techniques. Okay, so based on this practice, I hope it can kind of remind your memories, recall your memory, right? So the partition function of the bisolids has natural log z equal to this stuff, all right? So please show the Helmholtz function can be written in this ugly form. Okay, let's go. So what is F for the bisolid? The bisolid is also a three-dimensional spring oscillator model. So your F, we have known that 3 minus 3 n kt natural log z. Remember where we got this, right? Remember where we got this? Here, right? Okay, so final page. So F equal to minus 3 nkt natural log z, so we can substitute this here. So the rest of it are all calculus, all right? Careful. 3 nkt 9 u minus 3. You know, in the first year of my teaching, I didn't mention this example because I just said, you can go back to you can go back to your home and then practice by yourself. And then your seniors keep asking me about these questions. And then, okay, I just include it into our teaching material. 听得懂吗？我是说啊，之前我都没有，第一年的时候我是没有讲这一题的。我想到你回家自己练习啊，因为反正大一都教过啦。但是啊，所有的学长姐都一直问我说：“哎，这题怎么算啊？这题怎么算？”我说：“好，算给大家看。” OK， 所以实际上这一题就是没什么，就是都纯粹都是微积分啊。但是因为太多人问啊，所以我想说，好吧，那就其实算这个蛮无聊的，就是纯粹都是数学。那我就只是等于说把详解写在这里，让大家回去在算的时候有点依据。Okay, just saying that this is kind of boring, but I need to, I think it's better to write down all the detail of the solution to help you to recall your memory of your calculus. So you can see that it's changing variables of the integration. Okay. Right. So continue. 3 nkt 9 u cube. Zero u natural log 1 minus exponential x dx3 divided by 3. Okay, so at this point, everything becomes difficult because you need a relatively advanced technique called integrating by part. It's called integration by part. Okay. So this natural log of 1 minus ex is a, and then d dx3 over 3 is bx. Okay. And what is integration by part? A d b equal to ab minus b d a. Wow. Recall that, right? We learned that in the first year of your bachelor degree. And then V and K. And the rest of it is kind of cumbersome, too much. But I still need to write it. Sorry. 下面就是比较可怕的算式啦哈，虽然很无聊，但是就是希望你们就不用自己，也不是不用自己算，你要自己算哦，然后你要看一下我是怎么算的，然后我相信多多少少可以帮助你们。OK。这个部分，哎，真的很可怕。有时候我都在想啊，哇，这个东西为什么要学那么难的东西呢？我跟你说了哈，其实学这些东西，对我们来说就是重训的感觉。你去想想看，我们大家最近应该都知道重训的必要性嘛，哈，维持健康的必要性。那你会说，我们平常需要举那么重的东西吗？哎，是不需要啊，但是它可以让你变得更强壮啊。所以这个东西也是一样，这些东西就是我们的很重的哑铃哦，然后平常不会用到，那它就锻炼我们的头脑，然后平常做什么事情就会比较轻松一点。I just saying that doing this, it seems like useless because we haven't used that in the future. We won't use that in the future. But to me, it's just like a weight training, just like a workout to make your body or make your brain get used to the difficult task, so you can make your daily life easier. All right, done. Okay, so I just want to say that this example, three parts, three things I need to focus or emphasize. The first one, the F. The F is three-dimensional oscillator. So you need to know where we obtained this result, right? In the previous few pages. Okay, and then after you substitute these natural log things, V, and then you find that the X need to be changing variable, right? Changing variable to make the integration continue. Okay, so after doing that, you end up this. And then you'll notice that you can using integrating by part to solve this. So integrating by part is A and B is equal, integration A and B is equal to AB minus B dA. So it's kind of changing, swapping the integration. And then you continue to do that and then do again the changing variable. And so you can finish that. All right. So this is the 16.5. Yeah, I guess, yeah, you need to review your calculus techniques and yeah， 好，我们要讲的就是这一个题目有3个地方要注意。F 呢就是的表示是哈，它是3D 的振动子，所以你从哪里来的呢？就前面几页啊，我们就可以算出来了。所以还要先算 S 啊，然后再算 F 啊，这很辛苦的哈。有了这个东西以后呢，再把这个东西带进去。好，带进去以后呢，我们就会发现积分到后来你需要变数变换 ，OK， 变数变换，所以这是第一个我们需要提供给你的，就是微积分的技巧。然后积分到后来发现，哇，糟糕，又记不下去了。有一个好工具叫做 integrating by part， 叫做部分积分。部分积分它可以让你就是A 抵 B 的积分变成 B 抵 A 的积分 ，OK。好，然后就算出来，继续算，然后又要再用一次转换变数，然后得到这个式子。那我们刚刚讲过啊，这很辛苦了哈。那大家加油一点，大家常常都有听到我的教师评量的那个回馈单上面写说，我的课都是材料系最难的课。我是不知道啦哈，但是对，的确是蛮难的。那如果你今天可以克服这个课程，在这个系上，在这个科目得到好成绩，表示说你在这个系上最难的课也可以得到好成绩啊。那我祝福大家。OK，Thank you for your cooperation and maybe see you next time. 拜拜。有问题可以来问我。说，
所以你看里面说上课讲这个是好的，然后我看前面的是这个很小，
对，没有错，没有错，
因为我看
没有错，没有错，
刚这一个小，
对，是小 n， 是小 n， 三小 n r， 3小 n， 谢谢老师。那不，谢谢你，然后我要给你加分。好，请告诉我你的号码。
哦，313
313 614 013。好，谢谢。
老师，你作业有忘记写符号的，
作业
最后一页
最后一页帮你写符号，哪里？看一下。
中间的这个部分这边放写
啊，对，好
然后这边也是
啊，对
微分微错
啊，对，很好。对，这边要再多写个符号，对不对？这里啊，哦，对，这边也要负的，
对，
真是的。这样，
对，
还有没有别的？
没有
好，感谢你给我你的号码。
313
313
613
613
105
105。
对，
好，谢谢。
老师。
好，谢谢。OK。耶。